Hello, my name is Cameron Ackerman, and today we are going to talk about uncertainty in stage-discharge relationships. In this presentation, we will provide you with an introduction to stage-discharge uncertainty. We will discuss stage uncertainty as it pertains to stream gauge locations. We'll discuss uncertainty as related to computed water surface elevations and combining stage uncertainties. And then we will show you how to input a stage discharge function with uncertainty into HFDA and discuss its use for evaluating with project conditions. Core guidance requires that risk analysis be performed for any planning study. In order to perform risk-based analysis, we need to have stage discharge curves and a definition of their uncertainty. At a minimum, you must perform analysis for the existing conditions without project and the with project conditions. Because we must create a relationship with project conditions, we most likely will need to develop a river hydraulics model to develop a mean stage discharge relationship and define the uncertainty about the rating with a probability density function. This probability density function, or PDF, is characterized by a mean and standard deviation using either a normal, triangular, or log normal distribution. Impact areas are used by FDA to group or aggregate structures together when considering flood damage. We aggregate this flood damage through an impact area to a specific location called an index location. Impact areas are defined by economic type, such as by agricultural or urban areas, and further by hydraulic conditions, such as that the water surface can be used consistently for the computations. These hydraulic conditions consider constant slopes or consistent slopes, river formations, overbank areas such as levees that may lend the river system to react quickly to changing water levels. For risk and uncertainty calculations, it is necessary to aggregate damages to these index locations in order to be able to quantify the uncertainty in the calculations. We have to aggregate the damages to these index locations so that we can run risk and uncertainty calculations using Monte Carlo simulation procedures to determine the risk and uncertainty. Monte Carlo simulations require running tens of thousands of runs. Therefore, stage discharge relationships with uncertainty bands are required as input for each of these locations. We can develop stage discharge curves from observed or measured data or through computed water surface elevation profiles. Typically, we don't have a long enough record to be using observed data, so we have to compute water surface elevation information through river hydraulics modeling. Based on those water surface profiles, we are then able to develop a stage discharge rating information. Modeling can be performed through either steady flow analysis, unsteady flow analysis, or multidimensional modeling. Because modeling is likely to be performed to develop this stage discharge relationship, it's important for us to identify and attempt to quantify the uncertainty associated with the modeling parameters. The modeling parameters most likely to affect results are listed here: terrain data, roughness factors, hydraulic structures such as bridges and culverts, levee overtopping and breaching, debris and other obstructions, sediment transport, scour and deposition, bed form changes, and backwater effects.